Hello and welcome. This is the first video in the chapter 22 PowerPoint slides on electric charge. Electric charge is the fundamental uh, quantity. It's a fundamental physical concept in the entirety of Physics 2. Everything that we will be building up to in this chapter can, in one way or another, be related to electric charges and ultimately the fields that cause them to move. And so obviously you can kind of see in this picture here, we've got all this lightning shattering from the clouds. I mean, during a thunderstorm, right? During a thunderstorm, all the molecular collisions in the clouds cause ions to form, and those ions are electrically charged, and enough ions build up. Clouds are really big balls of electric charge. If they get, big enough, they can have such a large charge that they have to discharge either inside of it or discharge to the ground. Electric charge is all around us. The device on which you're listening or watching this video is only possible because we were able to harness the electric charge inside the device, inside the components that make up the device. So we can have some different parts light up. We can have different parts vibrate for sound. We can have different parts send and transmit and store information in a specific way. Okay, a lot different from Physics 2. Physics 1, Physics 2 is really a concise and logically developed theory about electric charge. So we start innocently enough with a series of experiments, and these experiments kind of show us some ideas about electric charge. Now, don't get me wrong, I think a lot of us come into the Physics 2 with the idea that opposites attract and like charges repel. Okay, and we'll get to the atomic source of electrons and protons in a minute, but here I want to kind of give you some experiments, and you'll be confronted with some sort of strange possibilities in this course of experiments. So for most of these experiments, we have some rods. We have some plastic rods, and we'll also have some glass rods. Actually, we'll have some wool, we'll have some fur, and some metal balls, some glass, some kind of plastic balls. But this is our control experiment. Okay, this is where we start from in Physics 1. Right, we have two rods, and we haven't done anything to them. Okay, they're there, and they don't have anything. They don't feel any attraction. They don't feel any repulsion. Some of you snooty types might think that there's a small gravitational attraction between these two. Yes, there is, but I mean, we can't, it's too small to measure, and we'll actually see that electrical effects far outweigh gravitational effects. Okay. So here's the first thing that we see. Okay, when we rub one of these rods with another, we find there's this repulsion. Okay. When we have rubbed both of these plastic rods with wool, then we see that the effect of rubbing both of them with wool creates some sort of electric repulsion. We don't say electric repulsion, we just say there's some sort of repulsion, some sort of repulsive force that these two rods that have been rubbed with, separate but identical pieces of wool now exert on one another. Okay, so this is kind of our first starting point for what is this thing? Okay, so when both of these plastic rods are rubbed with different but identical strips of, or little pieces of wool, we see this repulsive effect. And so this should be kind of alarming because, it's kind of confusing. Well, now we bring in a second possible contender here. We have plastic that's been rubbed with wool, and then we have glass that's been rubbed with silk, actually. And if the plastic is rubbed with the wool and the glass is rubbed with this different silk, then it turns out that when you bring the plastic and the glass together, they attract, as opposed to the previous slide, with plastic repels, plastic with glass attracts. And furthermore, if you, experiment 4 dictates that if you increase the amount of vigorous rubbing or vigorous friction against these two, there is more force. And also in this case, if you increase the distance with them, the force is less. So more rubbing of these rods means more electric force. And if they're further away, if they're closer together, the force is larger. If they're further away, the force is less. So those are some kind of empirical things that we could use to actually do experiments to sort of create a relationship between the two. Now, if you go back to this third slide or third experiment here, where you had the glass with the plastic, okay? If you just take a step back, before they knew about the atom and before they knew about the electron and the proton and that there were only two charges, this should be very alarming, because you can imagine, I mean, even back maybe a couple hundred years ago, how many different categories of materials were there? There might have been glass, there might have been different types of textiles, there's definitely been wood, there would have been metals, right? Think of all the materials that are possible now, actually. How do you know which ones will attract and which ones will repel? That's kind of the confusing thing about the concept of charge from the very beginning, is that if there isn't a finite number of types of charge, then you can't really create a theory to explain which two combinations of objects rubbed with other objects will in fact attract or repel, or maybe even do nothing. So that makes it kind of confusing. Like, what if we brought in a third pair, like rubber and styrofoam, right? Imagine like a styrofoam ball. If you take a blown up balloon, you rub the styrofoam on it, right? What's the styrofoam going to do to the plastic? What's the styrofoam going to do to the glass, right? And so there's no real theory that we have to describe what that's going to do. Keep in mind, this is all conceptual, okay? Yeah, but here we have a couple of another experiment which really throws something else more confusing into the mix, and we formalize it in the following experiment 6. But experiment 5, what we do is we just rub a comb through our hair, and suddenly you can pick up little strips of paper, maybe little tiny pieces of hair or dust. I don't know about anyone else, but I made the mistake one time of leaving my wool coat during a dry winter day, leaving my wool coat on the floor, carpet, right? Carpet probably could have used a vacuum, because when I picked my wool coat up, sure enough, there's tons of stuff on it, right? Little pieces of fur, maybe not fur, little pieces of dust, little pieces of hair, little pieces of all this stuff, little strips of whatever. I mean, so even objects that have been rubbed together, they can even pick up objects that seem not to be charged. And we formalize it with this one, right? If a rod has been rubbed and you bring it to another rod that hasn't been rubbed, the unrubbed rod will actually feel an attraction. So that's what's interesting about electric charge, is that even though an object is not electrically charged, it can still feel an electric force. That's kind of the general takeaway of this experiment. We haven't quite defined like electric charge yet, but that's what we're getting after, is that not only do opposites attract and not only do like charges repel, but charged objects attract electrically neutral objects. That's what's fascinating, and that's what makes kind of these experiments that we're trying to do to see if an object is charged or not, that's what makes them really interesting. So that's experiment 6. And we got a quick little question here. I'm going to go over that skip that real quick. So what about the two objects that were rubbed together themselves? The previous experiments were just talking about separate rods charged with separate, pieces of glass or silk. If you rub the glass with the silk or the plastic with the wool, in this case, the plastic and the wool, you'll find that they attract. Okay, so the two objects that are rubbed together will attract when they're done, right? And this is the classic, do-it-yourself experiment where you can rub a balloon on your head. It's going to stick, right? You can do that. It's pretty easy to do. So yeah, objects that are rubbed together will have some sort of attractive effect on each other. And so that really brings to mind the role of friction. It turns out that friction in Physics 1, what was the point of friction in Physics 1? Well, what is friction anyway? I mean, friction is the result of two objects coming into contact and kind of their molecular bonds that come into contact with each other breaking. And that breaking releases energy, which in turn raises the temperature of them by the first law of thermodynamics, right? The first law of thermodynamics says that when you do work on an object, in this case, like rubbing your hands together, would be doing work on your hands, the temperature goes up, the energy increases. Well, we now see that friction plays another role of, for some objects, generating an electric charge on them. So friction can always increase the temperature of an object. Sometimes it might even generate an electric charge. And that's because, like I said, when you break molecular bonds, well, the bonds now are kind of ionic shreds of the molecule, right? So bits and pieces are charged. And so now you have bits and pieces that are charged here and there, and that's what gives an object its charge. All right, moving on. Here's the smoking gun, though, for why you have only two types of electric charge that we see. Right? If you go back to that imaginary table that I mentioned a few minutes ago, if you were to tabulate or think of all the pairs of objects that you can bring together if they have been rubbed together, right? Without this experiment, there's really no way to say whether or not you have two objects that will attract or repel. But experimentally, it turns out that if you have two objects that are rubbed together, maybe they're plastic with wool and then glass and silk, if you bring in a third object that has been rubbed by something else, say styrofoam and rubber, it's never true that a third charged object will attract both the other two. You will always have one of them being repelled and the other one being attracted. That is if the one in the middle is charged. That is if the one in the middle has been rubbed, as we're calling it. Okay, and so this diagram, it's a little bit misleading just because this situation is possible if the thing in the middle happens to be uncharged. If we go back to, if we go back to this, if we go back to this experiment right here, we see that the uncharged rod or the unrubbed rod is attracted to the charged rod. Well, now if you bring that uncharged rod back to in the middle here, you'll see that this effect is produced. So you will never see this effect if the middle thing is charged. You will see this effect every time if the thing in the middle is neutral. And so this right here is a summary of this charge model that we have. It's kind of fun to go through, define things as either having a plastic charge or having a glass charge. Think of things as, being how the objects acquire a charge, either by rubbing together or as we'll see in a minute, in contact with other objects. Okay, yeah, I mean this first video or two is really kind of a conceptual framework to figure out how objects actually acquire an electric charge. So, and this is in the textbook. All right, moving right along. In experiment 9, what's going to happen here? When we bring in, this is when we start bringing objects into contact with one another, okay? So in experiment 9, we have a charged rod into contact with this ball, okay? The ball is metal. So what's going to happen when this rod is this charged rod is brought into contact with this metal? Well, the metal is going to require a charge, and the rod will lose a little bit of its charge, and that charge will be transferred to the metal. Now, experimentally, it turns out that the charge that's on the metal, it turns out that the charge that was on the plastic or the glass, it goes to the surface of the metal. It doesn't go to the inside. It just all sits on the surface. Oops. There we go. Here's another experiment. If you take a charged rod and kind of rub your hand around it, then those strips of paper, those little pieces of dust or hair or whatever, they don't automatically leap up to the charged object like they did in experiment 5. Which, by the way, this experiment 5 would have been true if, it would have been true if the experiment was with the plastic or the glass, and south is the same thing here. It's going to be true if it's the plastic or the glass. And so all this experiment really demonstrates is that the human body behaves electrically like the ball of metal does. Okay, and we classify materials like this as conductors, and conductors are going to be, well, they're going to be pretty much the most important types of materials for us moving forward when we want to create electric circuits and create, radio frequency antennas and all those sorts of fun electrical devices. We're going to need electrical conductors. Okay, and here's the last pair of experiments that show that there are different types of materials. Okay, so in this first one, we have the two metal balls. All right, we have the two metal balls on their little stands, their little perfectly insulating stands, and we have a connector between them. Looks like it's a plastic rod or a plastic piece of connecting these two rods. And if we charge the one on the right by bringing it into contact with the charged rod, experimentally, what do we see? We see that the left ball, that the left metal sphere does not acquire electric charge. Okay, evidently, the charge that's given from the rod at the top here, top right of this picture, it stays on the right metal ball. It does not move through the plastic rod to get to the left metal ball. And contrast that with our final experiment here, experiment 12. And this is the 12th and final experiment. If we replace the plastic rod that's in between these two with a metal rod, then lo and behold, the electric charge that we give to the right one, it is shared between the left and the right one. Okay, so the charge, it doesn't, so the ball on the right, it doesn't give all of its charge to the left, but it shares the charges. It shares the charge, total charge given from the rod to the left and the right. And how much charge each of them gets depends on their size. These balls are identical, so they have the same amount of charge. If the left ball had, for instance, been bigger, I think it would have less charge than the one on the right. Yeah. But since these are the same, then you don't have to worry about that. So, and this final experiment, in contrast to experiment 11, right, shows that the difference between metal and plastic is that charge can flow through metal, and it seems to not be able to flow through plastic. And you repeat this experiment with glass, it'll have the same result as plastic. And so it turns out that we can automatically classify materials into two broad categories. One is a conductor, like metal, like the human body, which is really like a bunch of kind of ionized liquids, right? A lot of liquids behave pretty well like conductors. Pretty much everything else that you can think of, everything else, if you look out in your, look out in your home, you'll probably see most insulators: plastic, wood, glass, styrofoam, rubber, all these big categories of materials. They're pretty much all going to be insulators. So they're not going to allow charge to fly through them, but charge can kind of stick and be patchy from on different parts of the surfaces. Okay, so this has been a quick intro of the experiments at the beginning of chapter 22. They're really fun to kind of go through and think about. In the next video, we'll be a little bit more precise and talk about what we mean by electric charge. So until then, take care.